In today's functional analysis class, we are going to discuss projection. Projection. So first we define projection. A linear map P from a linear space X to itself is called a projection if P square equal to P. Now we discuss some properties of projection. So we write it as a remark. Remark 1. If P is a projection, so is I minus P. So we can prove this. Proof. I minus P the whole square of X is I minus P of X. So this is equal to I minus P of I of X minus P of X. So this is I minus P of I of X minus I minus P of X. That is equal to I minus P of X minus I minus P of X. So this is I of X minus P of X minus I of P of X plus P square of X. P of X. So this is equal to X minus P of X minus I of P of X is P of X plus P square of X. We know that P is a projection, therefore this is equal to X minus P of X minus P of X plus P of X. P square is P, since P is a projection. So this is equal to X minus P of X. So this is equal to I of X minus P of X. So this is I minus P of X. That is, we have started from I minus P the whole square of X. That is I minus P the whole square of X equal to I minus P of X. So this implies I minus P the whole square equal to I minus P. Therefore, I minus P is a projection. So if P is a projection, I minus P is also a projection. Now remark 2. Range of P is zero space of I minus P. So we prove this. Let X belongs to the range of P. Therefore, X is equal to some P of Y for some Y in X. So this implies P of X equal to P of Y. So this is equal to P square of Y. So this is equal to P of y since P is a projection. So this implies P of y minus P of x equal to 0. So this implies, you know that P of y is x. P of y is x. So this is x minus P of x equal to 0. So this implies I of x minus P of x equal to 0. So this implies I minus P of x equal to 0. So this implies x belongs to 0 space of I minus P. So we have started with x in R of P. So we have reached x belongs to I minus P, a set of I minus P. That is, x belongs to R of P implies x belongs to 0 space of I minus P. So this implies R of P is contained in 0 space of I minus P. Now we prove the reverse inclusion. You let x belongs to 0 space of I minus P. This implies I minus P of x equal to 0. So this implies I of x minus P of x equal to 0. So this implies x minus P of x equal to 0. So this implies x equal to P of x. So this implies x belongs to the range space of P. Therefore, 0 space of I minus P is contained in a range space of P. Therefore, if you take this as 1 and this as 2, from 1 and 2, a range space of P equal to 0 space of I minus P. Now remark 3, 0 space of P is range space of I minus P. Proof. We have I minus P is a projection. So in remark 2, you will replace P with I minus P. Therefore, by remark 2, range space of I minus P equal to 0 space of I minus P. So this is 0 space of P. So this proves this remark. 0 space of P is range space of I minus P. Now remark 4, x is equal to range space of P plus 0 space of P, and range space of P intersection 0 space of P is singleton 0 for every projection P defined on X. So first we prove that range space of P intersection 0 space of P is singleton 0. So proof. Let Y belongs to the range space of P. Then there exists an X in X such that Px equal to Y. So this implies P square X equal to Py. Now since P is a projection, this implies Px equal to Py. So since Px is equal to Y, you can replace Px here. So this implies Y equal to Py or Py equal to Y. That is, if y belongs to the range space of P, then Py equal to y. This is 1. Now let y belongs to 0 space of P. Then Py equal to 0. This is 2. Now, therefore, if y belongs to R of P intersection set of P, then from 1 Py equal to y, and from 2 Py equal to 0. Therefore, y equal to 0. Therefore, range space of P intersection 0 space of P is singleton 0 always. We are going to show that any element x in X can be written as the sum of two elements. First belongs to the range of P and the second element belongs to the 0 space of P. So let x belongs to X, and we have x equal to I of X, that is equal to P of X plus I of X minus P of X. So this is equal to P of X plus I minus P of X. So you let x1 equal to P of X and x2 equal to I minus P of X. Then P of x1 equal to P square of X, or P of X, so this is P square of X, that is equal to P square of X is P of X, since P is a projection, and you know P of X is x1, so this is equal to x1. Therefore, so this implies P of x1 equal to x1. So this implies x1 belongs to range space of P. Now consider x2. We have x2 is equal to I minus P of X. Therefore, P of x2 equal to P of I minus P of X So this is P of I of X minus P of X. So this is P of X minus P square of X. So this is equal to P of X minus P square of X is P of X, since P is a projection. So this is equal to 0. Therefore, x2 belongs to 0 space of P. Therefore, every x in X can be written as x is equal to x1 plus x2, such that x1 belongs to a range space of P and x2 belongs to 0 space of P. Therefore, R of P Z of P spans X. The set R of P, Z of P spans X. So this implies X is equal to R of P plus Z of P. Now we have one more remark. If Y and Z are subspaces of X such that X is equal to Y plus Z and Y intersection Z is singleton 0, then for every X in X there are unique Y in Y and Z in Z such that X is equal to Y plus Z, so that the linear map given by P of X equal to Y is a projection. It is called the projection onto Y along Z. So if Y and Z are subspaces of X such that X is equal to Y plus Z and Y intersection Z is a singleton 0, then for every X in X there are unique Y in Y and Z in Z such that X is equal to Y plus Z, so that the linear map given by P of X is equal to Y is a projection. It is called the projection onto Y along Z. So that's all for today.